Hi, in this video we're going to be talking about Chapter 14, Section 4, at which the first half will talk about tangent planes. Tangent planes is really the equivalent of the idea of tangent lines back in 2D. So just as a quick review, in 2D, we would have a curve on the xy plane, and we would want to find the tangent line through one of the points. So we'd have a curve f of x, and we'd have a tangent line at each point if it was differentiable. And that tangent line could be used to give approximations. It was used to talk about the slope at that point. That tangent line did a lot of work in Calc 1 or Calc AB. Now, in 3D, the last chapter, or last section, 14.3, should have shown you that we're not going to have as easy of a time talking about tangent lines, because on a 3D surface, we're going to have lots of different tangent lines. So in 3D, we have infinitely many tangent lines, right? If we have a surface and a point on the surface, I'll have tangent lines like, I'll have tangent lines going that way, I'll have tangent lines going that way, I'll have tangent lines going that way, and they could all be tangent to the curve at that point in the same way. So that's really not the right notion. Instead, it's going to be relatively easy for us using partial derivatives to talk about two special tangent lines. We have two special. So if my point is somewhere x naught, y naught, z naught, if my point is a special coordinate x naught, y naught, z naught, we can take a plane parallel to the y-axis. That's going to be x equals some x naught, and that'll give us some curve that's the intersection of that plane in that direction. And we can take that same curve, surface, and we can also take that same point and chop it in the parallel to the x-axis, so to speak, parallel to the xz plane. And that would give us a curve like this, maybe. Now, each of these curves, so this would be the plane y equals y naught. This is parallel to the xz plane. This is parallel to the yz plane. Right? It's backwards of what you might think. Holding the x coordinate constant traps the x, but allows the y and the z to remain free. And then we can get a tangent line in this direction. A tangent line to this curve might look like this. And then the tangent line in this direction might look like that. Because now we're back down to a 2D situation where we have a planar curve. We have a planar curve. We can talk about the derivative of a planar curve. So I know it's kind of hard to visualize, but all together now, that gives me, on that same surface, at that same point, it gives me some tangent line, one special tangent line in the x direction, one special tangent line, in the yz direction, let's say, parallel to the yz plane, one special tangent line parallel to the xz plane, And together, you might remember that we can use these two lines, not lanes, lines, to find the equation of a plane. And so if you visualize building a plane on top of this, we'd have a good notion of the tangent plane that's sitting on top of the curve at that point. Those lines aren't going to help it look any better. So that's what we're talking about. We're going to use each of these tangent lines to make a tangent plane. Now, if you're wondering what does this have to do with anything we did last section, this tangent line holding the x coordinate constant, this tangent line has its slope as f sub y. And this tangent line over here, where the y was held constant and we only allowed the x to change, its slope was f sub x. And so that's how partial derivatives are going to be built back in here. Right. The book does some work to show why you would find the coefficients we're finding, but I think this visual justification works enough that we can just go to the equation. But if you want to see a more thorough working out of why the coefficients of the tangent line will be what they are, feel free to see the book. So I will say one more time, just as a review or recall, the planar equation, our classic plane equation, was a times x minus x naught plus b times y minus y naught plus c times z minus z naught equals 0. And we could also turn that into just a general equation, ax plus by plus cz plus d equals 0, or equals d, depending how you phrased it. That's what a planar equation looks like in 3D. What I was saying on the last page, the book will show you how we can get rid of all these coefficients, but I'm just going to go right to the equation of the tangent plane, or an equation of the tangent plane for a differentiable function. Why does this function have to be differentiable? Function, because we're going to use the partial derivatives. Z equals f, and we have two variables. That's what makes it a surface. So we'll use through the point x naught, y naught, z naught. I'm sorry, usually we label the point. Okay, through this point, x naught, y naught, z naught, the tangent plane, we'll do z minus z naught on this side equals the partial derivative at x of the partial derivative in the x direction evaluated at the point x naught, y naught, times x minus x naught plus the partial derivative at x naught, y naught. We have to evaluate that to get the slope, times y minus y naught. Before you get freaking out, there's one dependent variable, z. There's two independent variables, x and y. Okay? X naught, y naught, z naught are all constants. Those are a point you have in mind. Before I go much further, I'll compare this to in 2D. We would have had y minus y naught equals f prime at the special x coordinate times x minus x naught. And I think you can see the equivalence between these two formulas. They both have a derivative because the derivative is telling us the slope. Why do we need two derivatives in 3D land for a surface? Because there's at least two directions we could pursue. A better question might be, why do we only need two? Why do we only need two derivatives? Why not use all the different directions? And it's because we only need two directions to give us a plane, right? You could go through the proof and say, oh, well, we have this direction, and that gives us the normal vector, right? And the normal vector is what we need to talk about a plane. But the two direction vectors, it works out to be this. We'll have a nicer proof when we talk about a higher dimension version of this in a future section. But for now, this does just fine, I hope. I also want to say we can solve for z. If you solve for z, we can get z, it's usually written in front, z naught plus f sub x at that special point, x minus x naught, plus that same y stuff, and we can call this the linearization, fancy term, of f of xy at x naught, y naught, z naught. Sometimes we'll call it L of xy. Okay, just to symbolize it's a different function with two variables, two inputs, and one output. So let's do a couple quick examples here. Example 1. Find the tangent plane to the paraboloid z equals 2x squared plus y squared at 1, 1, 3, at the point 1, 1, 3. All right, so in the language of the theorem, or the language of the equation, that's x naught, that's y naught, that's z naught. Okay, you can verify that if I plug in 1, 1 to this function, to this surface equation, I will get a z coordinate of 3. What do we need to do? We need to find our partial derivatives. That's our main job. Partial derivative of z with respect to x, you can use whatever notation you want, will just be 4x. The partial derivative of z with respect to y is going to be 2y. Okay? So, in the notation of the theorem, f sub x, and we want to evaluate it at 1, 1, would just be 4 times 1, or 4. And f sub y at the x coordinate and the y coordinate we picked was 2 times 1, which is 2. So the plane, the tangent plane, z minus the z coordinate equals the slope number for x times x minus x naught plus the slope number for y times y minus y naught. That's it. That's all we're doing. We're talking about tangent planes. I almost called it tangent lines. A linearization for this function would just be 3 added into the mix. We're just literally adding 3 to the other side. It's linear in the sense that the variables are all to the first power, to the first degree. That's what we're talking about. You could solve this for z. You could write it as a planar equation. You could simplify things out, but there's no need to. That's not really what we're interested in doing. That's it. That's us assembling the building blocks. Let's do one more example. Find the linearization of f of x, y equals spoilers, x e to the xy at the point 1, comma, 0, comma. Could you right now find out what the third coordinate is? Right? Could you right now find out what the third coordinate is? If I just said it like this, x equals 1, y equals 0. Yes, you would just do, well, okay, f of 1, comma, 0 is what? 1 e to the 1 times 0, which is just 1 e to the 0, which is just 1. This is the z naught. That's the x naught. That's the y naught up there. Okay? No big deal. We're just plugging into the original function. But that's the y, that's the x we're using. Right now, you should pause the video and try to find the partial derivative with respect to x and the partial derivative with respect to y. 3, 2, 1. With respect to x, we have to use the product rule because I have two functions with x multiplied. So that's first times the derivative of the second should have been a y e to the xy because I have to multiply by the derivative of the exponent, treating y like a constant, plus the second e to the xy times the derivative of the first, which is just 1. I'll write it. Okay? In the y direction, things are a lot simpler. It says y is a variable, and so the x's are constants. So it's as if we said 5e to the 5y. That derivative is just going to be 25y. So in this case, we're talking about x squared e to the xy. We're going to evaluate each of these derivatives at the x and the y coordinate, at the interesting stuff. So that's 1 times 0. Once I know it's times 0, do I have to go on? Not really. E to the 0 plus e to the 0 times 1. Just 1. F sub y, be careful with your labels. 1 comma 0 is 1 times e to the 0 or a 1. So this is a very boring tangent line function, very boring linearization. You could just go to linearization if that formula makes sense, but I always write the tangent line first, the tangent plane first. Z minus 1 equals 1 times x minus 1 plus 1 times y minus 0, which will mean the linearization 1 plus, you don't have to write the times 1. We usually won't simplify it more than we have to because of how we're going to use these to estimate errors or to approximate other sorts of things going on. Okay, one more example. I think this video is a little short on time, so we'll do one more example. And it's always good to practice our partial derivatives. Find the tangent plane to z equals f of xy equals x squared plus 3xy minus y squared when x equals 2 and y equals negative 3. Try this out. It's the same exact steps as the last one. Careful with your partial derivatives. Pause the video. Try it out. 3, 2, 1. All right. First step, I'm going to find out what my z coordinate is supposed to be, which is f of 2 comma negative 3, which will be 2 squared plus 3 times 2 times negative 3 minus negative 3 squared. That's 4 minus 18 minus 9, which is negative 23. Not the nicest numbers in the world. I want to find my partial derivatives. Holding x as the variable and y as a constant, 2x plus 3y. Reversing the situation, I'm getting 3x minus 2y. Why don't I have an x squared in the partial derivative with respect to y? Because I'm treating it like it says 5 squared. If it said 5 squared, the derivative is 25 is 0. The derivative of 25 is 0. Make sure you don't plug those into your equation. You need to find the actual slope of these lines at the point in question. So this is 2 times 2 plus 3 times negative 3. 4 minus 9 is negative 5. Same x and y value, slightly different situation. Minus 2 times negative 3. 6 plus 6 is 12. For a slightly more exciting, is really not the right word, tangent plane. Z plus 23, because I'm subtracting a negative. Negative 5 times x minus 2 plus 12 times y plus 3. And we're careful with our signs, our SIGNs. And that's all there is to it, really. It doesn't get much more complicated than that. Obviously, the function, the surface, could be a lot more complicated to take the derivative of. But if you have the derivatives, you have the partial derivatives, it's just a matter of plugging things in and keeping the work organized. Thank you for your attention. Watch the next video for a discussion of how we'll use this to approximate or to estimate the approximations of different functions. Thanks for watching.